You could create multi-threaded Java applications using its core API since Java 1.0. However, this model used system threads, which were expensive, and over time, it became hard to keep pace with businesses, which demanded high throughput and low latency. And even with thread pools, executor services, fork join, and others, it was difficult to keep up. And this problem resulted in the rise of asynchronous style of programming, which used system cores much more efficiently and gave the businesses what they wanted, including handling of back pressures. But again, it had drawbacks. And if you ever have written asynchronous code before, you would know that it's hard to write, maintain, debug, and observe. And if you disagree, when was the last time you reproduced a bug in that setting? So we have help with us, which is in the form of virtual threads and concurrent programming, which makes it easy for you to write, maintain, debug, and observe your multi-threaded Java code. But wait, do virtual threads change the existing thread model? And if yes, how does it affect your existing code? And does it work with the frameworks you're used to working with? And what are the places it doesn't help? I don't have questions to all these questions, but our guest today, Jose, definitely does. Hi, everyone. Thanks for joining in for another IntelliJ Idea live stream. I'm your host, Mala Gupta. And now let me add our speaker to the stream.
Thank you, Mala, for this introduction and for your invitation.
It's a pleasure for us and all the viewers right now, because it's a pleasure to be able to learn from you. Thank you so much for accepting the invitation. And before we move forward, Jose, so I want to ask you a quick question before I let you take the floor. So we have been talking about Java being able to support multi-threaded programming ever since its version 1.0. And I remember when I started to learn about multi-threaded programming, the one question that stuck was, even if I'm not writing my own Java programs, which are multi-threaded, I would be using threads in one way or the other. So does that apply to virtual threads as well? Because if anyone is not using virtual threads, would they be using virtual threads in some way or the other?
Well, everybody is interacting with threads in Java since the beginning, as you just mentioned, before the time of virtual threads and now is the time of virtual threads. So I would say, and it's completely transparent. You don't actually, probably for 90% of the developers around, you are running in a thread and you don't know about it. And that's probably one of the magic of the Java language, which is fully multi-threaded, but with not all the complexity exposed to you and exposed to your application, which is great. And this will be the same with virtual threads. So that's even better, I would say.
All right, so it makes sense for everyone to know about virtual threads, whether they are using applications or creating applications which explicitly use these. So that makes a lot of sense. And of course, let me quickly introduce you. I know you don't need an introduction but for anyone out there who doesn't know you, Jose is a Java champion, assistant professor at the University of Sorbonne, Paris, Java 1 rockstar, member of Paris Java user group, co-organizer of Devoxx France, and disorganizer of another conference. I'm not able to pronounce the name, so you'll have to help me with that. G
Chateau.
He's also the creator of popular series, which is Jeff Cafe, which you can find on Java's YouTube channel. Author and very popular and articulate speaker. So he's one person that I watch all the videos that you have on Jeff Cafe and a lot of talks as well. So I absolutely love the way you teach things. And with that, I would just mention a few of the housekeeping details for everyone who's watching. Please use YouTube chat to post your questions, and we'll try to answer your questions as you post them. We'll not hold them back till the end of the session. Jose will take breaks to answer the questions. And the session is being recorded and will be hosted on IntelliJ Ideas YouTube channel and also on JetBrains Twitch channel. So if you haven't already subscribed to our channel, now is the time to do so. And if you like today's session, which I'm very sure you will, please like the video and so that you don't miss similar content. And with that, Jose, I'll let you take the stage and have fun.
Okay, thank you, Mala. I used to be an assistant professor at the university in Paris, but actually I joined Oracle 2 years ago as a Java developer advocate in a Java platform group. So we are going to talk about concurrent and asynchronous programming, and that's the spectrum, the scope of the Loom project, which is a project that has been under development in the OpenJDK for something like 5 or 6 years, I think. And before we start, I just would like to advertise something we're doing. Here are some links to the content that I'm publishing, including my GitHub account and YouTube channel and this kind of thing. And in the DevRel team at Oracle, we also handling a website called dev.java, which could be your one-stop place for everything related to Java. And we're also publishing a lot of content on YouTube and on other things. And I would like especially to shed some light on the Inside Java podcast, which is a great podcast, a set of interviews with the people that are actually developing things in the OpenJDK. And there are at least 3 episodes on Loom and on VirtualThreads that you may want to listen if you're interested in these topics. So what is Loom about? Loom is about bringing a new concurrent programming model to the JVM. If you take a look back, the first concurrent programming model was in Java 1, 1995. The second one was the first major update of this programming model was in Java 5, 2004, with the introduction of the executor service, the callable, which is a model for your tasks that is now the first model was the runnable itself, and then a callable came in, plus many other aspects in a concurrent space, and also a very important piece of code, which is the executor service. Starting with Java 5, you're not supposed to launch your threads by hand anymore. You're supposed to use an executor service, which is a pool of thread. Basically, you submit your tasks to this pool of thread. This task is going to be executed in a thread handled by this pool of thread, and what you get in return is a future object that allows you to interact with the task that is running in the background. And also, the synchronization model went from the synchronize keyword in Java 1 to a bunch of concurrent primitives like lock, reentrant locks, count latches, cyclic barriers, and more to handle the synchronization of your application. So that's 1995, 2004. Then 2014 was the release of Java 8 with 2 very important APIs, a second pool of thread called the fork join pool, which works differently than the executor service. The executor service is a pool of thread, and there is one waitlist for all the threads. That is, if you submit a task to this executor service, it will go in this waitlist, and all the threads are going to take one task after the other to execute it. The fork join pool works differently. Every thread has its own waitlist, and when a thread is not doing anything, it can take a look at the other waitlist of the other threads and take a task from these other waitlists. This pattern is called the work stealing pattern, and it's implemented in a fork join pool. And then there is another concurrent API added in Java 8 in 2014, which is the completable future API. And this completable future API is the first attempt at bringing an asynchronous programming model within the JDK. And that was 10 years ago. So every 10 years, something is happening in the concurrent space. First release of Java, Java util concurrent, fork join pool, completable future. We are 10 years after that, and Loom is beginning to publish what it has been working on. So I would say that the Loom train is exactly on time. So what is Loom about? I would like to show you an example, which is here. We're going to go directly to the IDE. And here I'm I created a city object. This city object is just a record, whatever. And I have this the static method here that is going to query a web server to read the weather for this city. So what I'm doing here is preparing the request. Okay, I'm going to align that so that you can see it properly. So I'm preparing the request here. I'm getting the response from the server, and then I'm decoding the response. The prepare request is just this method. So it's basically creating this HTTP request. It's basic HTTP code in Java. It's creating this request with a JSON object, preparing the request, and returning this request object. It doesn't launch the request itself. How much time does this piece of code is going to take to be executed? Probably in the order of the tens or probably hundred of nanoseconds, because it's just actually in-memory computation. The marshalling of my object, of my city object, to a JSON object, that's in memory, or the creation of this request object is also an in-memory computation. So let me go back to the calling code, which is there. Now I'm launching this request object on the internet. Okay, so actually it's not going on the internet, it's a local web server that is going to be queried. Okay, and I'm sending this request somewhere, and here I have a network request. This request is going outside of the memory of my virtual machine. It's actually going on the internet. And it's not working in the same order of magnitude. Here we are talking about milliseconds, because that's how networks are working, in the order of the tens to 100 milliseconds. So the preparation of the request was a computation, was an in-memory computation taking nanoseconds. This request is taking milliseconds. There is a factor of 1 million between the preparation of the request and the request response itself. And after that, when I have the response from my HTTP request, I'm going to decode it. And the decoding of this response is kind of the same as the previous one. It's again a JSON unmarshalling, and it's again an in-memory computation, so something that is going to take probably between 10 nanoseconds and 100 nanoseconds. So once again, something that is in the order of magnitude of 1 million times faster than the request itself. So when I take a look at this code, here I have something that is going to take, let's say, 100 nanoseconds. Here, something that is going to take 100 milliseconds. And here again, something that is going to take 100 nanoseconds. Okay, that's the order of magnitude when we take a look at this code. Now, the question I would like to ask is twofold. First part, what is my CPU doing when I'm running this code written in that way? And the answer is my CPU is busy for 100 nanoseconds, is waiting for 100 milliseconds, and busy again for 100 nanoseconds. Okay, so basically my CPU is doing nothing. If I monitor the utilization of my CPU, what I will see is about 0% utilization of the computing power of my CPU, which is a pity. Okay, if I show you a diagram for this one, that's actually what it's going to do. Here on the green part, first green part, that's the marshalling of my JSON, the creation of my JSON object, then waiting for my request to be launched on the network and my response to come back. And then when I have the JSON response, I unmarshal it to recreate my Java objects. And that's, again, nanoseconds. So if I'm just using one thread to run this kind of code, basically my CPU is idle 99.9999% of the time. It's not doing anything. Of course, a CPU is an expensive stuff to buy or to rent. So I would like to use it like 100% of the time, just to make sure that I spend my money well. So the question is, how many threads do I need if I want the CPU to be busy 100% of the time? And the question is quite simple. If every thread is using it 0.0001% of the time, I basically need 1 million threads to keep my CPU busy. All right. Is it possible to have 1 million threads running on a platform? Then we need to understand what is the price of running one thread. It turns out that in Java, a thread, an instance of the thread class, is actually a thin wrapper on the kernel thread. So the price of a thread is actually the price of a kernel thread. The kernel thread is a system resource, an operating system resource. It takes about 1 millisecond to start a kernel thread, and it will allocate about 2 megabytes to store its own stack every time you create a thread. Okay, so it means that if you want 1 million of such threads, it will take you about 1,000 seconds to launch them, which is between 15 and 20 minutes, which is a lot. And you will need about 2 terabytes of memory in your machine to be able to store, well, to provide the memory these threads are needing. 2 terabytes of memory is a lot, certainly much more than the memory I have on this laptop. So it's just not possible to do that on simple machines. Okay, so the solution that could be, let me run this code in many threads so that I can keep my CPU busy, at least with kernel threads, is not a viable solution. It's not a solution that you can actually use because you would need a much too powerful machine to do that, if it is possible, which is probably not the case. So the solution that people decided to use is actually the following. Instead of, sorry, I'm going to go there. Instead of writing the code in that way, which is imperative synchronous code and blocking code, because this thread here is doing nothing on this method call. What is called is blocking. Okay. People said, okay, we are going to break this code in elementary operations, and we are going to launch them asynchronously. And the following method, this one, is actually the same method, but written with the completable future API. Now, the completable future API is not the only API that you can use to write asynchronous code. Sometimes people have came up with better syntax. In other language, they even came with some language feature to create asynchronous code, but the idea is always the same. You need to gain a factor of 1,000,000 to keep your CPU busy and to make it so that your threads are actually working when they are executing your code. And this is exactly what this completable future API is doing. You go asynchronous. This is a Lambda expression that is going to be executed sometimes in the future, not when you run this code. And then when the city object has been marshaled to JSON, this JSON object will be fed into this method. This is also a Lambda expression, so it's not executed when you run this then apply method. It's executed later. And the execution of this method is actually triggered on the availability of this JSON object. Now, it's not too bad because this JSON object will be available very quickly in the order of the nanoseconds. But then this request will not block the thread that is going to launch it, okay? Because it's asynchronous, and the same will be executed on this following then apply. This Lambda expression will be executed when the payload from the response object is made available, so that the JSON object part of the response of the HTTP response will be used to unmarshal and to recreate this weather object. So this is the pattern that has been introduced now probably a little more than 10 years ago, yes, which is asynchronous programming. Now, what are this pattern of code is working, and it has been working for 10 years, and it has been solving this kind of performance problem for 10 years, but it has a cost. The first cost is that it's probably not as readable to write the code in that way, and this is a very simple example. Okay, it's probably not as readable to write the code in that way than in the classical imperative. Sometimes people say boring way, but in boring there's also simple and easy to understand. It's not easy to unit test because it's not always easy to know in which thread every every task is going to be executed. All this is going to be executed in an executor service. But what thread of this executor service is going to be used? This you don't know. So creating correct unit test is very hard, and it's super hard, if not impossible, to profile. What you're really profiling when you're profiling this kind of code is actually the framework that you're using, and not necessarily your code. So if you have some kind of performance issue in your code, it's very hard to know if it's coming actually from your code, from your business code, or from the framework itself. So this kind of solution, even if it's currently working, it's not ideal. And so the Loom project that has been launched about 4 years ago aims to explore the second solution of this problem, which is, okay, we need to gain a factor of 1 million just to have 1 million thread. Okay, could it be possible to create another model of thread that would be less expensive to create? Okay, here we have threads that are launched in 1 millisecond. And if we do that, we can only probably have several thousands of threads on a server. And this is the amount of thread you can launch on your machine if you try to do that. If you need 1 million thread, it means that we need to come with a model of thread that is actually 1,000 times lighter. Instead of having megabytes, having kilobytes or tens of kilobytes, and instead of having a starter type of 1 millisecond, having a starter type of one in the order of the microseconds. If you can reach that, then it means that you can have 1 million threads on your machine, and then this code, this blocking imperative code becomes viable because it would be running on threads that are much lighter than the current kernel thread. And this is exactly what Loom is doing. And I would like to insist on this factor 1,000. If what you're gaining is only a factor 100, then it's not enough. Okay, if you're making threads that are 100 times lighter and faster to launch, it just means that you will still have to use the asynchronous programming model because it's not enough. It will be good, but not good enough. So this is exactly what Loom is aiming to do, and this is what Loom could achieve. Having a new model of threads called virtual threads that is much lighter than the kernel thread, and that you can launch in a very short amount of time, in the order of the microseconds, and that will consume much less memory. So I would like to show you how you can create these threads and how you can run them, because it's super simple. So I'm going to do that. This is actually this thread.offPlatform factory method unstarted task is a new pattern that is introduced as part of Loom to create a platform thread. Now, platform thread is a kernel thread, it's just a regular thread, and the thread class is the same as the class you've been knowing for years. It doesn't change anything. And if I run this code, I have here, let me hide this, okay? I have here a runnable that is just printing the current thread. So if I run this code, you will see that what I'm doing is just, I'm just launching a thread, and this thread is called this stuff, okay? That's the name of the thread, and that's just a regular thread that you've been using for a while. Now I'm going to copy this code and paste it there, and just replace this off platform with off virtual. And this is how you create a virtual thread. You need to use this factory method from the thread class to create a virtual thread. The object you get is an instance of another class called virtual thread, and I'm going to show it to you. This class, this virtual thread actually extends the thread class, the regular thread class, but it's not public. So you cannot compile code that depends on this class directly. You need to create a virtual thread through the use of this factory method. Right. And if I run this code now, okay, you see that I have, so this is not platform, this is virtual. Oh, yeah, whatever, never mind. Okay, so this is my platform thread, regular thread, and this is a virtual thread. Okay, this is the string of character you will have when you have when you create a virtual thread. And you can see something is that this virtual thread, number 23, is actually running on top of another thread, this one, which is a thread taken from a fork join pool 1, and which has the name worker1. And this is how virtual threads are working. A virtual thread is actually a thread that is running on top of a platform thread called the carrier thread in this context, that is taken from a fork join pool. Now, this fork join pool is not the same as the common fork join pool that we've been using for parallel streams, for instance. It's another fork join pool dedicated to running virtual threads. Okay. All right. So now that I have this model of virtual threads, how many such virtual threads can I create, and how are they working? So I'm going to use another piece of code here. This code is just there to create some kind of a loop, and here it's a loop just with one element in it. And the runnable that I'm using is this piece of code there. Okay, I'm just displaying this thread, printing this thread just for the thread of index 0. Then I'm blocking for 20 milliseconds, and we'll see why I'm doing that. Okay, and then I'm printing this thread again. All right, and I'm going to do it one more time and one more time. Now I am, and one more time. So now I'm printing this thread once, 2, 3, 4 times, and I'm blocking this thread 3 times. And I'm going to run this code first with one thread. And you can see that I basically have the same message as previously. That is, this is the thread 22 that I'm looking at, and it's running on top of the carrier thread that is always the same. Okay, so let me add another thread. Let me put 2 threads, and I'm still looking at just thread 0. I'm not interested in the other one. So it's still thread 22, and it's running on top of the same platform thread. So I'm going to run it again, because this is not what I want to show you. Okay, now I have a proper result. And you can see that the first run before the call to thread sleep, this virtual thread is running on top of the worker 1, and then this virtual thread is blocked. And then when it's running again, so when it's executing this piece of code again, now it's running on top of the carrier thread 2, worker 2. And then it's blocked again, and then running on top of the worker thread 1 again, and then on top of this worker thread 2. Okay? And what you're observing here with only 2 threads, we didn't observe it with 1 thread, but we are observing that with 2 threads, is that this virtual thread that is wrapping a task, which is a runnable, can actually run on top of one carrier thread, and then on top of another one, moving from one to the other, while it was actually blocked in the thread.sleep. If I put that, if I run, let's put 100 threads, you can see now that it's working on top of another worker thread, the 7, the 1,000 threads. The 1,000 virtual thread is close to the limit of the number of virtual threads I'm actually running. Let me run it again. 1497. You see that this virtual thread is actually jumping from one worker to the other in this fork join pool, and that's for 1,000 threads. Let me put, I don't know, 100,000 threads. That would crash almost any machine if it was not, if there were platform threads. But you see that 100 virtual threads is okay. Fortunately, I'm not disconnected from the session. I'm still there. So it's working perfectly well. Remember that the goal is to launch 1 million of them. So okay, let me try with 1 million. And you see that 1 million virtual thread is okay. All right. It's still running, but at least the thread 0 is done running. The other are probably still busy. And this virtual thread has been jumping from one carrier thread to the other. That's the, I would say, the magic of these virtual threads is that they are not tied to a particular platform thread. So a virtual thread is just like a wrapper on a task, okay? And because this virtual thread can run, well, can jump from one carrier thread to the other, it means that this task can actually be detached from its carrier thread with this intermediate object, which is the virtual thread. And this is completely new. Okay, in Java, it was not possible previously with platform threads to detach a task from a platform thread. If you give up to Java 20, if you give a runnable to a regular thread, to a kernel thread, you have three solutions. First, this task completes normally with the result, if it's a callable, or it throws an exception, or you interrupt the thread. But there's no other way you can detach this task from this carrier thread. With virtual thread, it's not the case anymore. A virtual thread can be actually detached from its platform thread. How is it working? I'm going to show that to you. Okay. At the core of it, there is, and I'm going to visit this thread.sleep method. So here I'm in the sleep method, and you see that I have two pieces of code. One which is dedicated to virtual threads, and the other one which is not. So here I'm doing a virtual thread sleep nanos. By the way, this is using pattern matching for instance of one of the nice features recently added to the JDK. So let me visit this sleep nano method. I'm still in the thread class. Okay. Here I'm doing do sleep nanos. This code here is a code dedicated to JFR. If some of you are using JFR, this is some code for you. And if it's not, it's doing do sleep nanos. So let me visit that again. Let me continue. I'm in a private method, so I'm still in a thread class. And here I'm running. I'm running here this try yield method. So let me visit this one. I'm still in the thread class. Okay, and here I'm calling this yield continuation method. I'm still, of course, in the thread class. And here I'm calling continuation.yield. And this continuation object, which is not an object that is exposed by the API, so you cannot play with it directly, is actually doing this magic. This continuation.yield is where this magic is happening. Let me show that to you because we can play with this continuation object. Okay. To be able to create a continuation, I need a continuation scope. I'm not going into details in that. And what I'm going to do here is just print. Sorry. Okay. Print. Running. All right. And here I'm just calling run on this continuation object. So I'm going to run this code. It will probably yell at me, yes, because this continuation class is actually in the JDK internal VM stuff. So it means don't touch this class. So if you want to just see what it means, you need to add this magical code in the execution of the stuff. This basically said, hey, I am doing a demo. Please let me access to you. Okay, run this code again. Oh, thank you. Now you're okay to run, which is fine. And just say I'm running. So if I call run on this continuation object, you see that it's just executing the task, the callable, the runnable, sorry. I added that there. So now I'm going to do the same here, but I'm going to call this continuation.yield and pass this scope as an argument. This is what is happening. This continuation of the yield. This is what is being called in the sleep method. So let me run this code again, and you see that actually yielding a continuation suspend the execution of this code. This message I'm still running is not executed. And I didn't put it, but if I run this code there, back from run, see that it's going to be displayed on the console. You see, so this yield.scope is just as putting a return in the middle of the method, but this code is compiling. So it doesn't mean that it did not return, it just really suspended this stuff. And if I call run again, and add this message after that, and run this, you see this very unexpected, well, not expected, but very bizarre behavior. I run the continuation, so this code has been executed, and then continuation that yield was called. So it just suspended the execution of this runnable and went back to here, back from run. And then if I call run again, then the execution of this runnable is launched again, but it's not launched from the beginning. It's launched from the place where it was. Okay, and this is exactly what is happening in this sleep method. So what is happening when we're doing that? Well, actually, you are in this situation. There is your platform thread. Your platform thread is running a virtual thread on top of it, and whenever this virtual thread is blocked, it could be blocked on a sleep, could be blocked on some IO operation or on some synchronization operation. There is a call to continuation.yield, because this is this continuation object which is actually running this virtual thread. And yield is actually, let me go there, is actually copying some kind of passivating the stack of this virtual thread in a heap memory, thus freeing this platform thread from this virtual thread that is not doing anything, and that will be available to run another virtual thread. Okay. Calling yield is just like calling, telling the system, the JVM, the system, hey, I don't need the CPU anymore because I'm waiting from some data. I'm waiting for something that is going to happen from some event, and this event hasn't happened yet, so you can put me somewhere else. I'm not going to use the CPU anymore. And this is what this yield is really doing. Okay. And then when you call run again, then run will take this piece of memory from the heap and will put it back on this platform thread. Now, it will not put it back directly in this platform thread. It will actually put it back on a wait list of this platform thread within this fork join pool. Because remember that this platform thread is actually a thread from a fork join pool. And what is going to happen is that if this platform thread is actually busy, and there is another platform thread close to it that is not busy, this other platform thread will actually implement this work stealing stuff, that is, take this task, take this virtual thread, and execute it on another platform thread. And this is exactly what we are saying when we are running this code there. Let me run it again so that you can see it again. Right? You see that here, when I have a million thread, actually the thread 0 is jumping from one thread to the other, because when it's sleeping, it's just passivated in a heap memory, and when the counter for the sleep method is done, it will be signaled and then brought back from the main memory. Okay, and this is how virtual threads are working internally. So now the question is, how many platform threads can I run on this CPU? Okay, so I'm going here to, I have a different task, which is this one. I'm just reading, let me bring back the console, by the way. Where is it? It's not here. I think it's this one. Oops. This one. Okay, lost. Okay, this one was 4. Okay, never mind. You see, so here I'm going to, this code there is just analyzing the string of character to extract this number here, and I will just add all the numbers of worker thread for the million virtual thread I'm going to launch and put them in a set which is this pthread name set here. So let me run this code. Now I'm not waiting anymore. Okay, I'm just launching these virtual threads full speed. I got 1 million of them. And you see that even if this laptop is like 5 years old now, launching 1 million virtual threads plus all the software that is running in the background for the live stream, it takes about 4 seconds for 1 million threads. Okay, so 4 seconds, it means that it takes 4 microseconds on this busy machine to launch a single virtual thread. And you see that I have 12 cores on this machine, and only 12 platform threads have actually been used. So 12 platform threads is actually enough to run 1 million virtual threads, which is super great. Okay, I see that there's some activity on the channel, Malaf. So maybe there you saw some questions that I should answer.
Yes, there are a lot of questions. So let me start with the first one.
Yeah, absolutely. I should have asked you earlier.
No, that's okay. I didn't want to interrupt you. So there's a question by Basler, and he wants to know about more details about how the I/O event interacts with the virtual threads. When our I/O is done, the virtual threads get resumed. How? I think you just mentioned about continuation, and I'm unsure whether that would answer his question or not.
Okay. Maybe, okay. So actually, this continuation object is handled by a handler. And all the Java I/O and NIO API has been refactored so that when there's a blocking call, there is a call to continuation.yield. Okay. So all the JDK API has been refactored to do that. Now, when is this continuation.run going to be called? Actually, there is a handler that is registered on the operating system events. And when the data is there, there is a signal that is sent to it. And this handler will in turn called a continuation.run. This is how these things are working internally. I don't know if it answers the question.
And he had a follow-up question regarding the fork join pool. And his question was, how does it work with the virtual threads?
So the virtual threads are actually using threads from the fork join pool. It's a specific fork join pool. It's not the same as the common fork join pool that is used for parallel streams, for instance. And every virtual thread is handled by a carrier thread taken from this fork join pool. And as you saw on this last example, this fork join pool is 12 platform threads. So that's actually the exact number of cores I have on my laptop. And I have another machine with 16 cores. And I can see that this fork join pool is actually 16 taking 16 threads. So there's no need actually to have more platform threads than the number of cores you have on the CPU, which is just great because it means that it's going to limit context switching, which is an expensive operations when you're doing concurrency.
Right. And I'm sure you would have kind of heard similar questions like this, that would Project Loom kind of make another technology obsolete? So this is a question about, does Project Loom mean that completable future was a failure?
No, completable future. I mean, asynchronous programming was not a failure. I mean, it's a technology from 10 years ago. And 10 years ago, there were plenty of technology that were made obsolete by the new technologies developed as part of Java 8, which is fine. All right, we are working in an industry that is using new technologies, and there are new ideas and new implementations and new capabilities now and then. I mean, moving a 10 years old technology to the obsolete space is probably makes sense. I mean, it's not the only one that has been done like that. Plus, I mean, it doesn't mean that asynchronous programming is done. there are plenty of applications that are using that, and I suspect that they are not going to be rewritten just because people don't have the time or the resource. So they'll continue to run, and that's fine. It's just another tool in the toolbox to solve certain problems.
So there was a follow-up comment on this. So it mentions, as we're about to see, the code for computable future is more complex. So are there any changes to the API that we're talking about here as a
I
result of the
don't think
introduction
there's
of?
I'm not thinking of any change of the completable future API, because along with this technology of virtual threads, another stuff is coming, which is called structured concurrency. That will basically allow you to write the code I just wrote, this kind of code in an asynchronous way, but written without any callback and using imperative programming. Okay.
And
So
there's
there's no. Sorry. If you're using virtual threads and structured concurrency, you should definitely stop using asynchronous paradigms and asynchronous patterns, because it's not meant to work in that way. But it doesn't mean that you will not be using asynchronous code anymore, just because you don't have the resource to rewrite everything. It's just like when lambdas were introduced, right? It's not because you had suddenly had lambdas that all the code that was not using lambda that could was rewritten overnight. That's just not possible.
that makes sense, and that's a very good analogy. And let me know when you want to stop answering the questions, because I have tons of questions for you, and new ones are coming in. So whenever you want me to stop, I will stop. So,
okay, let me take one more question, and I would like to show the structured concurrency pattern so that people can have a look at what's coming next, and that they have hopefully a good understanding of virtual threads.
Right. So now that you have are on this code, there's a question which is related to this code, which is decode response form executed in the same thread as get body from and prepare request for?
Okay, so that's precisely the point. The answer is you don't know. And the information is not on the code you have in front of you. Okay. By default, I didn't configure any executor service there. So by default, it's going to be executed in a common fork join pool. But there are 12 threads in the common fork join pool. What thread is going to execute what task? Answer is, that's the choice of the common fork join pool. So basically the question is you don't know. And that's probably an issue, because if you want to write a correct unit test, you need to check for the result of the lambda in the same thread as this lambda has been executed. And if you don't, you have a race condition within your unit tests. And you may have bugs in your unit test that will just say, oh no, the result is not correct, and it's just a concurrency issue. And that's a problem. That's a problem.
That's interesting. So I'll let you move forward with your rest of the session.
Thank you. I would like to show you actually I didn't even run this code. Well, whatever, it doesn't matter. I just launched a Spring Boot app. I would like to show you also, where is the Spring app? Here. Okay, that's the class, the Spring app class. Where's my mouse? Okay, it's here. Okay, and that's the piece of code from Spring Boot that you can use to configure the Spring Boot application. Okay, and you have this method. This bean here is commented. So I'm going to switch to this wonderful HTML page. And as you can see, I'm a great HTML designer. All right, and this service is actually taken care of by this Spring Boot app, which is there. And here I just created a service that is going to print the thread that is answering to my request. Okay, and I'm going to refresh it several times, and you can see that I'm actually in a pool of thread. Okay, and if I run this code several times, you see that the thread exec 8, 2, 1, 3, 4, 5, 6, 7, 10, 9, 8, 2, 1, 3, etc. You see that I'm actually looping over the threads of a single executor service. The second thing I would like to show you is this code, API exception, which is actually just launching a null pointer exception to show you the stack trace. So that's my code. Okay, Loom app, that's me. All right, this part of the stack is actually the Spring Boot stack. Okay, so it's quite big, as everybody knows. There are plenty of things in it. And at the bottom of it, you have, or at the top of it, I don't know, you have this thread.run stuff here. Let me zoom on it. Okay, which is actually showing you that you are executed in a platform thread, in a run method of a platform thread. Okay, so I'm going to go back to this code. That's the one. I'm going to stop Spring Boot and activate this bin there. And this bin just tells Spring Boot that to handle HTTP requests, Spring Boot should execute this executor service. Now, this executor service, called new virtual thread per task executor, implements the executor service interface, but it's actually not a pool of thread. It's just creating a virtual thread every time a request is sent to it, every time it receives a task, basically. So this executor service is empty. It creates a virtual thread on demand and let it die at the end, because a virtual thread is a cheap resource. You don't need to pull them. That wouldn't make sense. So let me run the Spring Boot server again. Okay. By the way, you can see that it's just working, which is great. Okay, let me go back there. I'm going to show you the current thread again. And you can see that now this current thread is a virtual thread, and it keeps increasing. Okay, and it's always running on top of the same platform thread. Right? So this is how Spring Boot is working on top of virtual threads. And if I take a look at the exception, so same as previous one, here I have my stack, the stack of my application. That's the same stack as the previous one. Okay, until here, I guess. And at the very bottom of it, you can see that you have actually this JDK internal VM continuation enter. So you're actually executed by the continuation object I just showed you a few minutes ago. So just to tell you that actually Spring Boot, even if the JDK 21 is not there yet, it's around the corner really, but it's not there yet, Spring Boot is already ready to run on top of virtual threads, which is great. So a virtual thread is going to be a final feature of the JDK 21 to be released in September, which is great. And the structured concurrency part is going to be a preview feature. Structured concurrency has been released about a year ago as an incubator feature. Now it will be moved to the previous feature. And I would like to show you just one pattern, and I just have a few minutes for that to show you how it's really working. So basically, you have a scope object, which is a structured task scope here. Okay, and I'm going to say that it's a structured task scope of quotation. And the scope object is actually auto-closable. So I'm going to surround it with resources here. And it works in that way. It has a fork method that is going to take a task. And the task I'm going to call is this one, quotation read from A. I'm just going to add double colon there because it's a longer expression. And I'm going to do it with read from A and read from C. Okay. The scope object is working almost as an executor service. You submit tasks to it, and in return, it will give you, sorry, on this version that I'm using, which is version 21, it's a future object. On the next version, on the preview version, it will be a different object, a task handler object, which works kind of the same as the future object. So here I get a bunch of futures. When I'm done forking tasks, I'm going to call fork scope.join. Okay, and this join method will block until all the tasks that I've submitted to this scope object are done. And once I have this, I could, for instance, on future one dot result now, and then okay. I could also analyze all the results of this future object, get a mean, because this is a quotation, so there's a sorry, it's a record, so there's an amount in it, and so I could just return the quotation that has the smallest amount, but that's let me just play in that way. And this is basically the pattern you want to follow when you're using structured task scope. 3 steps. First step, you fork all your tasks, and they are going to be executed in a virtual thread within this scope object. Then you call join, and this join will block until all the tasks are done. Either they will produce a result or through an exception. And when you're done with that, you can analyze the result through your future object. You can also do that within the scope object, because you can extend it and then produce a result. And the biggest difference between this way of writing things and the classical asynchronous way is that it's completely synchronous code. It's synchronous imperative code executed in a current thread. All your tasks are executed asynchronously in a virtual thread created by the scope object, and the scope object will let this virtual thread die after that. And all your code here is imperative and blocking. But because blocking a virtual thread is cheap, it's okay to actually block it. Okay. And the second biggest difference with the executor service pattern this time is that you can see this scope object as some kind of executor service. The only difference is that its life cycle is not the same as the executor service life cycle. An executor service is an object that you launch with your application and that you let die when you shut down your application. The scope object is an object that you create when you need to launch a task asynchronously. And here, this read quotation is itself an asynchronous task. And once you're done with this computation, you just shut down this structured task scope, you close it. This is a try with resources statement, and you garbage this object, because this scope is a local variable. So when you exit this method, this scope object will be garbaged. So this structured concurrency is a preview feature in the JDK 21. There will most probably another preview feature in 22, due in March. So there's still a work in progress. If you want to participate, if you want to have feedback, suggestion, comments, etc. on this kind of pattern, you should need to connect to the mailing list of the Loom project on openjdk.org to provide your feedback. Okay, and I think we still have 2 minutes for more questions, Mala, right?
Yes, we do. So first of all, thank you so much. We have so many questions. I really have to see which one I can ask.
Okay. Try to merge them.
I was
maybe there are questions that are common.
Yes, you're right. So there's another question, and because there was a lot of follow-up comments on that question, so this is about how does it relate with event loop systems like Vertex? Does it make Vertex obsolete?
So does it make Vertex obsolete? That's a tough question to answer, actually, because if you're using Vertex and you invested a lot of time and wrote a lot of code, you're not going to give up Vertex just tomorrow. Now, Vertex is part of the important projects that are currently working on virtual threads and trying to figure out how they can leverage virtual threads to bring better performances for the patterns of code they offer. So that this is what they published. Will it make it obsolete? That's the same question as the question we had with lambda expressions, right? Lambda expression, 10 years later, they clearly have changed the way we were writing code 10 years ago. So virtual threads and structured concurrency are probably going to change the way we write asynchronous applications in between now and in 10 years from now, but it will not happen overnight. This is just what we can say, I think.
Right. That makes sense, because one of the other comments by the same person was probably it seems super complicated, and maybe I'm better off to stick with event loop ODEX and don't need to deal with multi-threading and a lot of follow-up comments. So I'll skip taking up, as you said, because that's going to change how we do a lot of things, let's say 1 or 2 years down the line.
Yeah. Absolutely.
Right.
Event loop doesn't necessarily make sense when you're writing blocking and imperative code. It makes sense when you have very small tasks and when you divide your whole process in very small tasks. But if you don't, then maybe event loop doesn't make much sense in the end. So maybe they'll change that, or maybe they'll keep it for other reasons. I don't know, really. You need to ask the Vertex team for that.
Right. So I'm not sure whether I should be asking anyone from the Java JetBrains team regarding this question, because multiple questions on how Loom compares with coroutines in Kotlin.
So that's a question for the Kotlin team also. I suspect that the Kotlin team knows about Project Loom. Would be surprised if they didn't. And so I guess they will probably try to do something to leverage what Loom is bringing to improve the patterns in Kotlin. I'm not very comfortable answering this question, because I'm not a Kotlin expert, far from that, and I think it would make sense to, or maybe have a discussion with the people from Kotlin just to compare things and compare point of views and performances and this kind of thing. What I hope is that the introduction of this new, again, it's a tool in the JDK, and the introduction of this new tool will help improve all the ecosystem, actually, and including Kotlin, of course.
Of course, that makes sense. And I'll add probably a link to one of the presentation that Roman did on talking about Loom, and also about coroutines to the description of this video, because I could see a lot of questions on comparison. So I'll do that later. And
what I think is important, if I just can add something on performances, because I understand that performances is a very sensitive and tricky topic, actually. I think that take your asynchronous code, like completable future code, running on top of VirtualThread, and comparing the performances with and without VirtualThread. I don't think it's the right way of comparing things. I think that the right way of comparing things is that, okay, we solved this problem with this technology, completable future, and we had this throughput. Now, let us rewrite this code synchronously, in a blocking way, in an imperative way, with boring code, no asynchronous stuff, anything, no callback, on VirtualThreads, and now we compare everything: performances, maintainability, readability, writability, testability, and we just make our minds. And I think that's the fair way of comparing things, because it's not only about performances, of course, it's also about maintainability of your code in the long run.
Absolutely. Maintaining an application or even debugging it, observing it, those are big part of any application. And your answer makes a lot of sense. And I would highly recommend anyone watching it, that's the way to go and go about comparing applications and performances. So there was another question regarding a lot of questions. Which one should I take? Okay, so this is about Python, comparing something in Python. I would skip that one. So this is about, will virtual threads flatten the future syntax, and will the compiler sequence execution of subsequent and sequentially looking code once virtual thread completes? Does that make sense? Because to me, okay.
You know.
That's okay.
Does virtual thread flattens future syntax? I'm not sure to understand that exactly. Will the compiler sequence execution of subsequent? With a compare sequence. Oh yeah, execution association. I'm not sure. I'm sorry. I'm not. I'm not sure to exactly understand the question. Sorry.
No worries. So there was another question about rewriting the weather example that you showed with virtual threads. I'm sorry, I was monitoring the question, so I couldn't kind of answer this
Absolutely.
question.
So it's actually, if you check my GitHub account, you will see the weather example and the quotation example to build a travel page, all written with structured concurrency and virtual threads. So if you just check my GitHub repo, and you will find the example. And yeah, it's it brings a much simpler. Actually, the patterns of code for the quotation stuff is exactly the same. It's just executed within a structured concurrency object, which make it possible to write imperative and blocking code. It's fine to do that. So it's actually the same. It's just the context of the execution of this code which is different.
And this, I think this one is a good question. The person is asking about details, whether they could find changes that were made to the JVM and ideally to the standard libraries as well to support the virtual threads. So they could, I guess, access the Java language specification. Would that be a good?
If there are any precise documentation on that, probably in a release note of the Loom project, I'm not so sure. So I won't make any bad answer to that. But just to quickly answer it, so all the APIs of the JDK have been updated to support this continuation object, so that every time there is a code that is blocking, there is a call to continuation.yield and stuff. There is a second thing that has been modified, which is that because you have now portions of the stack in a heap, all the garbage collectors need to know that. So all the current garbage collectors in the JVM have actually been partially rewritten to go and check in the heap what's going on exactly. So that's the second thing. And I think that's the two biggest part of it. Virtual thread, oh yes, and this continuation stuff is using, of course, C code, well, native code to move memory back and forth between the heap and the stack. That's mostly it, I would say. The pull request has been probably the statistics of the pull request when the first Loom version of Loom were merged in the main JDK branch has been published, and there was 100,000 lines of code added and modified to the JDK source code, which is a lot.
Which is huge. I think I read David's tweet on that.
Yeah, exactly. David Delabassi made a tweet on that.
Wow.
Can the structured task be run on virtual thread?
So am I
Absolutely.
still visible, audible? I'm not sure.
So yes, Thomas, structured task scope is running virtual threads, and you can use a virtual thread to run a structured task scope. Absolutely, it's made for that.
Okay.
Can I revisit the scope later? Well, you don't need to do that. Just don't pull the scope. Pulling a scope is useless. Pulling a scope is just like pulling virtual thread. Don't do that. It's useless. There's no need to pull a resource that is inexpensive. So just let your scope die and create another one if you did another one.
Okay, I think we are running out of time, but there is a lot of questions. But so I would add your GitHub link to your GitHub repo to the description of this video so that folks can access the content. And Andy Bailey, I want to give a shout out to him. He was answering so many questions. I think there was a question by this person, because I think that's the first time he's asking a question instead of answering all of them. But he's saying he may have missed this.
Yeah,
but
using using synchronized in virtual thread. Okay, you give me 2 more minutes to answer this one.
Yeah, sure. Sure.
I need 2 minutes. Okay, so moving this stack from one place to the other is only possible because in Java you cannot get an address on the stack. Okay. If you can get an address on a stack and you take this stack and move it somewhere else and bring it back in some other place, then you're doomed because you have an address on the stack that is not valid anymore. Now, the problem is that, the fact is that there are other languages like C and C++ in which you can get addresses on the stack. Okay. So if this virtual thread technology detects that in a stack itself of a virtual thread, there is a native call, it will actually pin these virtual threads on a platform thread. All right. So this jumping virtual thread that I showed you, you will not see it if you have a native call. Now, the synchronized block is not exactly issuing a native call, but there is, it's storing addresses on the stack because there is an array that is going to store the threads that are actually waiting on this synchronized block to be able to enter it, to execute it. So if you have a synchronized block in your virtual thread, in the code that is executed by your virtual thread, then this virtual thread will be pinned on a platform thread. Is it bad? And should you be doing something? The only thing you should be doing is check if it's actually an issue performance-wise in your application. Because in this synchronized block, what you're doing is just updating some variable or some kind of in-memory structure that you want to guard, then odds are that it won't be a problem in your application at all, because the pinning of this virtual thread will be very short, in the order of nanoseconds, so it will be okay. Don't do anything. Now, if you're doing some kind of I/O in this synchronized block, and your virtual thread is actually pinned on this platform thread for milliseconds, then you may want to do something. And the simplest thing that you can do is just to replace this synchronized block by a reentrant lock, which doesn't have this problem. Now, the people are fully aware of that. People from the Loom project are fully aware of that. They are working on re-implementing this synchronized block without this issue. So it could be solved in the future. No ETA on this one, of course, but this is the reality of it. So in a nutshell, if you have that, check if it's a real performance issue. First, don't do anything. Second, check if there is a performance issue. And three, if there is a performance issue, which may not be the case, then you can replace your synchronized block with a reentrant lock.
Thank you so much. So that's in French.
Merci, Thomas.
Yeah.
Thank you, Thomas.
Yeah. And there are a lot of other thank you messages. And thank you so much, Jose.
Okay.
It was an absolute pleasure to have you on IntelliJ ID live stream. And as
Thank you,
always,
madam.
great to learn from you. And everyone who's watching, please, you can follow these links to get more information. And the next slide is about, of course, if you haven't already subscribed to our channel, please do that now. Before we close, Jose, any closing comments from you?
Just, I saw also questions about demos and examples. Just check my GitHub account that you just showed the link, which is perfect, and you have resources there, demos and stuff on the Loom project, including a lab that will take you through everything we did together, step by step with the solutions. So yeah, definitely go and check that out.
That's amazing.
And thank you, Mala. Thank you for having me. Thanks a lot.
The pleasure is all ours, and everyone who is watching and listening. It was an amazing session. Thank you so much for presenting with us.
Thank you so much. Thank you.
Thank you. And and stay tuned for our next session, which we'll have next week. That would be by Rudy on integration testing on your server-side applications. So stay tuned, and we have more for you coming. And until then, bye.